only way you can put two logs together if they're added is if you put it back into one log with multiplication, but that's where we came from. So we'd be going right back to where we came from. But take a look at this derivative. This is not that bad. If I take the derivative of this, what's the derivative of that? -1, okay. 2 is a constant, comes along for the ride. What's the derivative of natural log of something? 1 over it, and then the derivative of what's inside? That's not so bad. What's the derivative? Let's see, -7 comes along. Derivative of natural log of something is 1 over it. Derivative of what's inside? 3x squared. That's not so bad, right? -9 comes along for the ride. Derivative of natural log of all this? 1 over it. Derivative of what's inside? 4x cubed minus 1. I don't think I had to do a product rule or a quotient rule or a chain rule at all, right? Not at all. Yes? I like it. You almost seem very like you all like it too much. But there is one issue. The left side of it is natural log of y. Because we introduced that, didn't we? So when I take derivative on the left side, what am I going to get? It's a derivative over here. 1 over y, drum roll, y prime. 1 over y times the derivative of y, which is y prime. And that's what we're trying to solve for, right? Equals, you just told me this was -1, right? Now it's calculus. Okay, plus 2 times 1 over cosine x times negative sine x. So that's derivative right here. Let's go around the room. Who wants to volunteer? We haven't gone around the room in a while. Go ahead.
For the next
This one.
2x squared. Oh, I'm sorry. 1 over x cubed plus 1 times 3x squared.
Good. But the -7, right? Okay, so -7 in front. Everyone good with that? That's the derivative of this one? We'll move around. Go ahead. What do you got?
So the next one would be -9 times 1 over x to the fourth minus x minus 1 times 4x cubed minus 1.
What should I do with this?
Or plus into the iron. No,
No.
it's on top, right?
Yeah, put it on top or put it in parentheses. It's a separate expression. So there's your derivative. That didn't require any massive computation, right? That was a lot. Would you all agree that's easier than what it looked like in the very beginning we were going to have to do? All right. I'm going to clean this up. Just a little bit, not much. What am I trying to solve for again? Y prime. I want to know what y prime is. What's wrong with the left side, though? It's not just y prime. It's 1 over y prime. So I'm going to multiply both sides by y. Okay, so here's what I've got. I've got y prime equals this answer, -1. What is this? What's sine x over cosine x? Negative tangent. So this will be negative tangent, and then negative. So we can just do this. -2 tan x. Can we do that? And then here, let's try and clean this up. 3, -7, x squared. So
7 over.
-21 x squared over x cubed plus 1. -7 times 3 times x squared, that's all on top, over x cubed plus 1. Here,
36.
you want to distribute that -9 through? I'm all for that.
X cubed plus 9 over x over x.
Now I kept it as a negative out here, and I distribute a +9 through. If you want to distribute the negative, it'll become positive here, negative here, and positive here. They would both be correct.
But now I have to do the y.
But all of that times y, right? All of this times y. So all of this times y. Oh, crap, though. What's y?
The main.
The original problem. Right? Y was the original function. So instead of putting a y here, I'm actually going to put e to the negative x cosine squared x over x cubed plus 3 to the 7th times x to the 4th minus x minus 1 to the 9th. That's y, right? That's your derivative.
Yeah, because you put it in and it's like, oh, why don't you simplify and take it out?
Yeah.
You really wouldn't.
You don't need to do any more. That's good. All right? That's an example of what's called logarithmic differentiation. So when is it that you know to actually pull out the logarithmic differentiation? When you see something that's the derivative is going to be really complicated, you've got a bunch of products or quotients and powers in there too. Looking back now at this, now that you know what we've done, do you see that we had quotients and then with the products and then a bunch of powers and how natural logs would help us resolve a lot of that? Yeah. Now in the book, when you get to the homework problems, they actually tell you use logarithmic differentiation to actually find the derivative of the function. So they kind of hint to you what you're supposed to do.
But on the test, it might just say find the derivative.
That's right. On the test, it'll just say find y prime. So, yeah. I would never ask you to do a derivative like that the traditional way. So if you see something you're like, oh my God, then you should be thinking maybe there's an easier way. Another example. I've always loved this problem. I've always loved that function because usually that's not a function that anyone's ever dealt with. X to the x. We're used to seeing things like x squared, right? X to the 5th. Shoot, we were even used to seeing square root of x, which is the same as x to the half. So seeing x to powers as functions, that's pretty normal, right? If we flip these and we do something like 2 to the x or 5 to the x or even 1/2 to the x, so all of these like change the role of what the variable is and the power is. These are examples of what types of functions? Exponential functions, right? So when the variable is in the base, it's a power function. When the variable is in the exponent, it's an exponential function. But what happens when the variable is both in the base and in the exponent? Then it's no longer a power function, it's no longer an exponential function. It's a function that you have never dealt with before. We don't really have a name for them. Because they don't have to be x and x. It could be, you could have a function that looks like this. Sine, no, I better not use sine. Well, I guess I could do that. Sine x plus 2. I got to keep it positive. Keep it from becoming a negative value down here. And then make the top cosine x. So I could do anything I want. I could do any function of x raised to any other function of x. And there's not really a categorical name that we use for these. Do you see the dilemma of this, though? Part of you wants to pull the x out. When I take the derivative, pull the x out and subtract 1. The other part of you wants to do x to the x natural log x. Or maybe not. Maybe the part of you just doesn't want to be here right now. I'm not sure what it is. You see, it's a kind of a conundrum. It's both situations at one time. We will use logarithmic differentiation for this. So with logarithmic differentiation, when we're seeing something like this, that's what's kind of hinting to us that we should come in with the log on both sides. So let me apply the logarithm to both sides of the equation. And what does that allow for on the right side? Allows me to drop the x out front. Because it's the power, I can pop it. So bring that power out. And now, if you're comfortable taking the derivative, we can take the derivative. Are you okay with taking derivative over here? Okay. How about here?
Yeah, is that a product rule?
That's a product rule right there. It's x times natural log x. So that should be pretty clean. The left side is 1 over y prime. By the way, that's always going to be the left side with logarithmic differentiation, always. Every time you use logarithmic differentiation, the derivative of the left side will always be 1 over y prime. You'll always have to multiply both sides by y when you're done. Always.
So you wouldn't have x on this, or you could have x on that side. I mean, the variable really doesn't matter, right? I mean, what's represented as.
If you've solved this equation for y, then you're always going to get 1 over y prime.
You have to solve for x, just change the variable. Or would it ever be solved for x?
It could be, but not, not. Yes, it could be when you're asking in terms of the big picture of math, yes. In a class like this, no. But see, if someone solves it for x, then are you trying to find the derivative with respect to x or with respect to y? Or, that brings other questions into it. Here, we're assuming we're taking derivative with respect to x. All right, right side, product rule. See if we can do this without writing out the little parentheses and the little prime marks. Let's just see if we can do this. Derivative of this is 1 times natural log x plus 1 over x times x. That's just going to be 1.
So it's just natural log x over right?
Plus 1. Plus 1. So we get 1 over y prime, or 1 over y prime is natural log x plus 1. Multiplying both sides by y at this point, you get natural log x plus 1 times y. And now replace y with whatever y was, which is x to the x. X to the x. Y prime equals natural log x plus 1 times x to the x. If you wanted to, you wouldn't have to. You could distribute through. Right? Distribute it to both terms. Either one of those would be fine. How about a little bit of U time? Yes?
How would the graph of y equals x?
Man, I was hoping someone would ask me that. And I was thinking I would graph it right now if I had a damn projector in here. I would graph it for you. Let's try and guess what it would look like, okay? We won't take too much time for this. You could just go to Wolfram Alpha and type x raised to the x and it would draw the graph. But first of all, we could not plug 0 in, right? Or could we? Sorry, x. What am I doing, Robert? 0. What's 0 to the 0? Dun, dun, dun. I thought 0 raised to any power was 0. But I thought anything to 0, I thought anything raised to the 0 was 1. It's a half, yeah. No, this is actually like trying to divide by 0. You can't do it. All right? So we can't plug 0. It's undefined. All right, but we can plug in 1. 1 to the 1 is 1. All right, that wasn't so bad. 2, 2 to the 2 is 4, 3, 3 to the 3 is 9. And then you can see this is almost acting like a power. Thank you. 4 to the 4, right? Now this thing is acting like a power function and an exponential function at the same time, right? Because both your base and your exponent are growing. So if we graphed it, I know at 1, it's 1. At 2, it's 4. At 3, it's gone. Well, at 4, it's gone, right? So it looks kind of like this, doesn't it? We think so far? If you were to graph some other numbers in there, I mean, I think we all agree it gets bigger, but what happens, what's more interesting is what happens like in between 0 and 1. Like what if you took 1/2? Then that would be 1/2 to the 1/2, which would really mean the square root of 1/2. What's the square root of 1/2? Well, that's the same as 1 over the square root of 2, which is the same as root 2 over 2 if you rationalize it. Like square root top and bottom is this, and then rationalize it, you get root 2 over 2. Root 2 over 2 0.707 something. So it's less than 1. So it would be in here. So it's acting a whole lot like maybe a rational, an exponential function. But remember, exponential functions came back and they tapered off and went this way, right? Can you do a negative number? What's negative 1 to the negative 1? It's 1 over negative 1 to the positive 1, which would be negative 1, wouldn't it? So that would work. Could you do negative 2? Negative 2 to the negative 2 would be 1 over negative 2 to the 2, which would be 1/4, right? But then what about negative 3? Negative 1/27th. So this one was negative, this one was positive, this one was negative, this one was positive. They would actually be jumping back and forth between positive and negative numbers. And then what happens at the fractions? And then things get really kind of messy. And it doesn't look like anything we've ever seen before. You asked. Yes, it's a very unnatural function. Most of the time, we wouldn't even want to look at it over here. When you take negative numbers and you raise them to negative powers, things get really crazy. Because, like, let me try and give you an example here. What's negative 1/2 to the negative 1/2? Right, that's x to the x. This means 1 over, so I'm going to convert that to a positive, negative 1/2 to the positive 1/2. Yeah? But what does 1/2 really mean? Square root, so that's square root of negative 1/2. Uh-oh. Imaginary number. You're not going to be able to do that. In fact, you won't be able to do negative 1/4, negative 1/8, any even, right? You're not going to be able to do, because it's going to require an even root of a negative number, which means that every fraction containing an even number, this thing gets real spotty over here, okay? There are parts to the graph, there are pieces that aren't there, and yeah. All right, we've got about 20 minutes. What's the homework assignment for this? We have enough time that we can proceed. Just double checking your homework assignment. Make sure you can handle all this. I really want you to be focusing on the homework for 3.3, right? The 3.2, that's kind of up to you. All right, 3.2 is a review of exponential and log functions. If you feel kind of about it, go back, take a look at that homework assignment on here. If you feel okay with it and you want to just move on, this is the one you need to do. This is the one that's kind of like depends on you. 62. Okay, yeah, there's one more type of problem that I should cover. No, this one's a cool problem. Find equation of tangent line to the curve x to the y equals y to the x at the point 3, 3. Yeah, so we go back to what we learned at the very beginning of this course, right? When we're talking about equations of tangent lines, you're going to resort back to this formula right here, right? You're always going to go back to that formula if you want the equation of a tangent line. The only thing is this slope, right, is going to come from the derivative. So we've got to be able to find the derivative here, and then we need to plug the actual point into that derivative. Luckily, we're given a point, right? This point does live on this curve. 3 to the 3 is equal to 3 to the 3. All right. But we need the derivative. So we need y prime. Where the hell is it? So let's find y prime. Put it up here. Okay, yeah, so what you have here is really a mess. We haven't seen this, right? You've got x to the y here, y to the x here. What are we differentiating with respect to? X? Everyone agree? That this is dy dx. That's what we want. The trouble is that we're assuming that x, like the derivative of x would be 1, right? But the derivative of y is going to be y prime. So I am not allowed to use power rule here. Like this is not x to the 4th. Bring the 4 down. Can't do that because y is not a constant. On the other hand, I can't look at this as a to the x because, again, y is not a fixed number. So since you can't do that, natural log on both sides. So let's take the natural log on the left side. Take the natural log on the right side. And that allows me to now drop both powers out. So the left side becomes y times natural log x equals x times natural log y. I have not done a derivative, now derivative, right? The left side, when I take the derivative, will be a product rule here. The right side will be a product rule here. Just the derivatives are going to be a little different, aren't they? What's the derivative of the left one here? Y prime ln x plus 1 over x times y. So the derivative of y is y prime times natural log x plus the derivative of natural log of x, which is 1 over x times y.
So it could be just straight y over x.
Y over x, yes.
Isn't one like not the inverse, but like
Is what?
not the inverse, like because we're changing variables and I don't know how to explain it. Like,
If you think of, if you're able to clarify it in your mind, just let me know. Okay. Over here, derivative of x is 1 because it's with respect to x times ln y plus now 1 over y prime times x. So again, take derivative natural log of y. This time it's 1 over y, derivative of the inside, which is y prime. See, we did the same thing here. Derivative of natural log of x is 1 over x times derivative of x. What's derivative of x? It's 1, so we don't include it. Here it has to pop out, the y prime. What are we solving for? Y prime. Do you see y prime in here? It's on both sides. So I'll clean up first. What was the standard protocol if we have this sort of implicit differentiation we're solving for y prime? After we've taken the derivative, what do? Everything that has y prime to one side, everything that doesn't to the other side. So I'm going to take the y prime natural log x, keep it on the left side. I'm going to take this one, bring it over, so it's going to become minus y prime x over y. And then on the other side, I'll have natural log y, and then I bring over the y over x to the other side, so it becomes minus y over x. Yeah, the whole point of that is to be able to pull the y prime out on the left side. So I factor out a y prime. And the last real step that I have to take now divide through that stuff in parentheses, both sides. So y prime equals ln y minus y over x over ln x minus x over y. You could clean this up, but you could, but we have what y and x are, right? Like, so since I know what y and x are, I can plug in and I can actually get my slope, right? So at the point 3, 3, y prime equals natural log 3 minus 3 over 3 over natural log 3 minus 3 over 3, but that's just 1. All that for a slope of 1. Or at least it wasn't 0, right? Then we would have to say all that for nothing. At least it was for 1. So y equals y minus 3 equals 1 times x minus 3. That's the equation of the line. And if you do your cleaning up there, you get y is x. So if you graph that line, it should be tangent to the curve at that point. Ten minutes. I think I've probably given you enough to get through the homework for 3-3. Yeah, just do what's there. Let's sign in today. Since we have 10 minutes, I will entertain the quiz, unless there's any other questions. You're free to go after you sign in, so y'all get that passed around quick. But I was asked about the quiz, so I'll hang out and try and work through this. Oh yeah. Anyone else for the quiz? I'm trying to remember the problem. And you're not going to hurt my feelings if you leave, all right? So is the circular track 50, 100 to here? This, we called it, did we call it X? We did call it X, and then no, we changed it to A, didn't we? Change it to A, little a, and this angle is big A. And then at the particular moment in time we were talking about, it was 50, 120, and 100. And I think I had even, was that all I gave you, or I just wrote what the formula was? Oh, the angular speed, right?
Everyone's signing in as well.
Okay, that's fine. Just sign in on 12. What we were given, did we find D capital A? 7/50ths radians per second. 7/50ths. And what else? We wanted d little a dt. We wanted it at exactly the moment that little a was 120. I think that's everything that we had before we left class. And I also put the formula up here for law of cosines, which was a squared equals b squared plus c squared minus 2bc cosine capital A. All right, that's everything you had before you left, right? All right, so all you needed was a formula that related this to this, which was there, except B and C. B and C were actually, you could call this one B. Let's take a vote. How many of you called 100 B? And then how many of you called 50 B? About half and half, so it doesn't matter how I do it. So I'm going to call B 100. I'm going to call C 50, all right? And so that formula up there actually becomes a squared equals b 100 squared plus 50 squared minus 2 times 100 times 50 times cosine of capital A. And there's a lot of constants in there, aren't there? Is that an equation relating capital A and little a? So I can differentiate that. So I'm going to differentiate that right now with respect to time. What's the derivative of a squared, little a squared? 2 little a d little a dt, right? 2 little a dA dt equals, what's derivative of 100 squared? 0. Derivative of 50 squared? 0. Negative 2 times 100 times 50 is a constant sitting in front of a function. It comes along for the ride. So what is that? 10,000? So negative 10,000. Derivative of cosine of this? Negative sine capital A times d capital A dt. What I am given and what I want both appear in there. And all I need to figure out the problem is what little a is, which I have. So really the only real thing that I don't have is capital A, right? Capital A is right there. See, and I can fix everything in time now. So since I can fix everything in time, that formula right here, right, this formula, I can actually fix this to be 120 squared. So I know 120 squared equals 100 squared plus 50 squared minus 10,000 cosine of capital A. Calculator time. All of this?
No, the first side.
14,4?
10,000,
And then 10,000 plus 2,500 minus 10,000 cosine A.
Yeah.
All right, and then you what? You put these two together first, right? And then subtract. So what does that leave you with? See, this is the type of math that just makes me go. It's just, my brain doesn't like to even do this stuff anymore, right? Don't you feel that way?
1900 equals.
1900?
10,000 cosine A.
1900, I'm trusting you, is negative 10,000 cosine A. And then you divide both sides.
By negative.
So I will need my calculator here.
And
Anyone disagree with these computations? Honestly, I'm not paying any attention to this. Yes? Okay. So we all agree with 1900 over? Okay, 1900 divided by 10,000.
so we're going
Reduce it
into
to 19 over 100.
What? What'd you say?
Can you reduce it by counting the zeros?
Well, it still turns out to be the same answer. It's still negative.
Yes, but I'm going to need to do an arc cosine, so I'm getting this ready.
over 100.
Yes. So 19 over 100. So negative 0.19 equals cosine capital A. Yes? Now you take the arc cosine on both sides. So make that negative.
0.76.
I need to switch myself into radian mode. You have to do that also. So we get, did I do it? Hold on, I don't think I did it. 0.19 negative, and then arc cosine. 1.76. 1.762 equals A. And that's radians, just FYI, rads. Okay? So that's your angle. It's that many radians. Now, if you did it in degrees, you should be okay because you're going to plug it in here, take sine of it, and it's going to spit back a number again. Now, are we sure that that's the angle?
Yes, that's what I got.
Okay, so let me try something real quick. I want to make sure that we're all looking at this properly because there is a little subtlety here that we have to pay attention to. Let me try something a little bit different. Okay, just hold this thought for a second. I still have a couple of minutes. If I told you right now that cosine of capital A was equal to negative 1/2, then I'm saying at what angle do you plug into cosine to get negative 1/2, right? If you go to your unit circle, the x-coordinates are your cosines, right? Where on the unit circle do you get an x-coordinate of a negative 1/2? Second quadrant? It'd be right up there, wouldn't it? What angle is that? Is that? Anyone know? It's one of the common angles. 120 degrees? 120 degrees? Right? That's not the only place that the x-coordinate is negative 1/2. It also happens down here, right? Okay, so all I'm getting at here is back in pre-cal, we did have to be kind of careful anytime we solved an equation like this using arc, cosine or sine on both sides. There was a possibility that we needed to look at two different angles, right? In this particular problem, it's not possible to have two different angles because this angle is 120, right? The only other angle here that we could get would be past 180, right? And our angle cannot be bigger than 180. Right? Because then we would be on the other side of the track. Okay, so when you're looking at this, let me try and show you an analogy, and I'll do it in green. When you say that cosine of an angle is negative 0.19, you're saying where on the unit circle is your x-coordinate, right there, negative 0.19. And it turned out to be whatever that is in degrees, right? There's another one down here where it happens, but that's past 180. So it's a subtle thing. If you did another problem where this had been like sine on both sides, and you did that, you'd probably have more things to be concerned about. All right. Keep going here. So you go through this. Let's see, 2 times a, so 2 times, it was 120, right, for little a? dA dt is what I'm trying to solve for. Equals negative 10,000 times negative sine of 1.762, and then what's d cap? 7/50ths. And then you take all of this answer and divide it by 240, and that's your dA dt. Anybody get the answer? Remember what their answer was? 5.7 something? 5.7 something? You got a different? Let me try this. Sine of that times. $5.73? 5.73 or something? Yeah, this looks like it's coming out to be about 5.73. How fast was she running? Was it feet? Was it feet or meters? It was meters? Meters per second. She was running how fast? Was it 7 meters per 7 meters per second? She is moving. It's Olympic quality there. All right, that's it, right? When's our test? Is it next Wednesday? No?
I think you told me
It's after, right?
from Monday.
Okay, yeah, you're right. Our test is the 26th,
Yeah, so a week from Monday.
a week from Monday. So next week will be trig, inverse trig, and L'Hopital's rule. And then the exam.
Just want to know I got it.